A vector is an arrow, so it has two characteristics, its magnitude or length and its direction. Probably the easiest type of vector quantity to understand is the displacement of one particle relative to another. Suppose that we have two particles. Let's call this one A and let's call this one here B. We are interested in the displacement of particle B relative to particle A. That displacement can be represented by a vector whose tail is at A and whose head is at B. We can write this vector like this here. The first letter is the tail, the second letter is the head. So this is one type of notation for a vector if we're given the names of the tail and the head of the vector. Now a vector has a certain magnitude or length. Let's say that the distance between these two particles is 5 meters. Now to denote the magnitude of this vector we could use vertical lines. So the magnitude of vector AB is 5 meters. How do we specify a direction for this vector? Well, let's suppose that we are dealing with vectors in just 2 dimensions, in the plane of the screen in this case here. We will use an angle to specify the direction of this vector. Now we need to measure that angle from a fixed axis. So the convention is that we measure it from the positive x-axis, which is an axis pointing to the right. And we measure that angle anti-clockwise from this axis. So in this case, for this particular vector, we have an acute angle. Let's suppose that this angle is 40 degrees. Now our vector AB is fully specified. We know its magnitude and we know its direction as given by this angle. For vectors in 2 dimensions we could also consider compass directions. The positive x-axis could be the easterly axis and the positive y-axis could be the northerly direction. So we can write the direction of vector AB as east 40 degrees north. So we imagine that we're at A, we face east and we veer 40 degrees north. Or we could use this angle in here, which is 50 degrees. So we could write our direction as north 50 degrees east. So we imagine we're at A facing north and we veer 50 degrees east. The velocity of an object can be represented by a vector. Let's suppose we have some object here and at a particular instant of time it's moving in this direction. Let's suppose also that at this instant of time the speed of the object is 2 meters per second. Now in the next instant of time, the next second, the next half second or the next millisecond, whatever, the object could be moving in a different direction and its speed could change. But let's suppose that at this particular instant its velocity is given by this vector here. So you can see that velocity involves more than just the speed of the object. It also involves the direction that the object is moving in at this instant. Now that direction again could be specified by measuring an angle anti-clockwise from the positive x-axis. Now we will see in later videos that when we are talking about vectors in 2 dimensions we can use a coordinate system to specify the directions of those vectors. For now we will just talk about this angle here. We could give this vector a name. We could use the letter V. Well, we can use any name of course, but if we use a single letter for our vector we need to put an arrow over it. We're not referring to the tail and the endpoint of this vector like we did for the previous example. Okay, so that's vector V. If we're interested in the speed, well, the speed is the magnitude of the velocity. Now the magnitude of vector V can be written in 2 ways. We can use vertical lines on either side like we did for the previous example, or we can just drop the arrow and write V without an arrow. So V without an arrow is the speed of the object, and in this case it's 2 meters per second. Now notice that the magnitude of a vector is always positive. It's always a number that's greater than or equal to 0. Okay, it's the length of an object. It can never be negative. Now we could imagine that the velocity of this object is constant. What does that mean? Well, it means that it will move in the direction of this vector forever. So it'll move along this path forever in a straight line with a constant speed of 2 meters per second. So for a velocity vector to be constant, the speed of the particle must be constant, and it must move in the same direction, that is, in a straight line with that speed forever. For the velocity vector to change, one of two things can happen. Either the speed can change, or the direction of the motion can change, or both can change. Both speed and direction can change. Another very important vector quantity is the acceleration of an object. Now this is actually the rate of change of the velocity vector of the object. Now we will see more about this in later videos. For now we will illustrate acceleration by considering the acceleration due to Earth's gravity. So this here represents the surface of the Earth, and here we have an object that's near the surface of the Earth. This object is freely falling towards the surface of the Earth. Let's suppose it falls from rest, so its initial speed is 0, and we know from experience that the speed will increase and keep on increasing until it hits the ground. If we ignore air resistance, we will find that all objects near the surface of the Earth fall at the same rate towards the surface of the Earth. So even if this object is a feather, it will fall at the same rate as a stone dropped from the same position from rest. So we got to imagine that there's no air resistance. Okay, so initially the speed is 0. At some later time, the velocity has increased from 0, and from some later time still, the velocity is even greater. And just before the object hits the ground, the velocity is at its maximum. So we can see that the velocity vector is changing. It's actually increasing in magnitude. It's not changing in direction for the case of an object dropped from rest. Now acceleration basically tells us how that velocity vector is changing. And for any object near the surface of the Earth, the acceleration has a fixed value. So the amount by which the velocity changes every second is fixed, and that amount is 9.8 meters per second each second. Now I will explain this in much greater detail in later videos. For now, we see that the acceleration vector, well, first of all, acceleration is a vector quantity. It's got a certain magnitude. For objects near the surface of the Earth, the acceleration due to gravity is 9.8, and it's got a certain direction as well. Actually, the direction of the acceleration due to Earth's gravity is towards the center of the Earth. Also, that acceleration vector is actually constant. So even when the object has fallen to this position here, the acceleration vector hasn't changed. It's still 9.8 meters per second squared. Anyway, we'll discuss acceleration in much greater detail later. The last example of a vector quantity that we will discuss is the force on an object. So we have some object here. Let's suppose that initially there are no forces acting on it, so it's floating in outer space. Suddenly a force is applied to it. So obviously we need a direction for that force. So force is a vector quantity. It's got a direction, and it's also got a magnitude. Okay, we can imagine larger or smaller forces acting on this object. Now force is measured in newtons, so we might be talking about a force of 2 newtons here. So this would be written 2n. We will see in later videos that the resultant force on an object and the acceleration of an object are related. Many other physical quantities can be represented as vectors, but we have covered the main ones that we will be discussing in later videos. For vectors in one dimension, there are only 2 possible directions. Now, to specify those directions, we use a straight line. Now, the straight line happens to be horizontal here, but it depends on the problem. In some situations, the straight line could be vertical, or indeed at any angle. So, in this situation here, one of the directions is to the right and the other direction is to the left. We use a plus sign for one of the directions. Typically, vectors pointing to the right are assigned a plus sign, and then we use a minus sign for vectors pointing to the left. Let's look at this vector here. I'm calling this vector A. Its magnitude is 4. Since it's pointing to the right, we could write this vector as plus 4. I've just put in the plus sign to emphasize that vector A is a vector that's pointing to the right. Now I've shown vector A on this line, but I can actually show it anywhere in the plane of the screen, provided that it's pointing to the right. So I could show vector A up here. These two vectors are considered identical as long as they point in the same direction. In other words, they're on parallel lines, and as long as they have the same magnitude. Here we have another vector that I'm calling B. Let's suppose that the magnitude of B is 2. So we could write B as minus 2. So the 2 indicates the magnitude, and the minus sign indicates that it's a vector pointing to the left. Again, I could show vector B anywhere in the plane of the screen. I could show it down here as long as its magnitude is 2 and it points to the left. Here is another vector which I'm calling C. Its magnitude is 1 and it points to the right. So we could write C equals plus 1. Now we can imagine multiplying a vector by a number. So let's suppose we take vector A and we multiply it by 2. Now this number 2 is a scalar. It scales the vector. It does not change the vector's direction. Well, actually, for a positive scalar, we do not change the direction of the vector. We do change its magnitude, however. So the vector denoted by 2a is a vector that's 8 units long and points to the right. So we've scaled our vector A by a factor of 2. We could also scale it by a factor that's less than 1. We could consider half A. Well, that's a vector whose magnitude is 2 and also points to the right. So I'll try to show that over here. So half A looks something like this. Its magnitude is 2. Now we can also consider multiplication by a negative scalar. Let's suppose that we take vector A and multiply it by minus 2. Now this gives us the vector minus 8. So this is a vector that points in a direction opposite to vector A. So here it is. Its magnitude is the same as 2a. We could, of course, just consider the multiplication of vector A by minus 1. We could write minus 1a, or of course we can just write minus a. So minus a is a vector that has the same magnitude as vector A, but it points in the opposite direction to vector A. Now let's look at the addition of vectors in one dimension. Let's take vectors A and C and add them together. Now for vectors in one dimension, addition is got by just adding these numbers algebraically. So we get the vector plus 5. So I can show that here. So it's a vector pointing to the right whose magnitude is plus 5. Well, magnitude is always positive. Now let's look at A plus B. So A is plus 4, B is minus 2, so we could say plus minus 2 here, or just 4 minus 2. That gives us the vector plus 2. So that's a vector pointing to the right with magnitude 2. Now let's look at vector C plus vector B. That's plus 1 plus minus 2, or just 1 minus 2, which is minus 1. So this is a vector pointing to the left with a magnitude of 1. Now what about vector A minus C? You might say that we should cover this situation under subtraction, but we can imagine vector A minus C as being A plus vector minus C. And we saw before that vector minus C is a vector pointing in a direction that's opposite to vector C, but both vectors have the same magnitude. But whatever way we think of it, we can think of it as an addition or as a subtraction. It doesn't matter, it will work out the same. A is plus 4, C is 1, so we get the vector plus 3. That's a vector pointing to the right with a magnitude of 3. Before completing this section on vectors in one dimension, I just want to mention a very important point. It's a point about notation. For vectors in one dimension, the arrow is often omitted. Now, in the next section, we will be discussing linear motion, that is, motion in a straight line. We will see quantities like u, v, and a. U and v are velocities. As a matter of fact, we'll see this other quantity s, which is a displacement vector. Now, for some reason, the arrow is omitted. It's omitted only for the case of linear motion, or which involves vectors in just one dimension. So if that's the case, how do we denote the magnitude of these quantities? Well, as they stand, they look like magnitudes, but it's very important to realize that these quantities are vectors in the section on linear motion. There are only two directions to consider, so those directions are designated by a plus sign or a minus sign. So u, v, a, or s could be positive or negative. If we want to discuss the magnitudes of these quantities, we will have to use vertical lines like this. We can't just drop the arrow and say we now have the magnitude, because the arrow was omitted in the first place. These are actually vectors. So even though we haven't covered velocity yet, I'll just mention now that the magnitude of a velocity is known as the speed. So the magnitude of u is the initial speed, the magnitude of v is the final speed. The magnitude of a, well, I could just write the magnitude of the acceleration. The magnitude of the displacement vector is the distance that the object has travelled, and that's always a positive quantity. But the displacement vector could be negative, We could have an object displaced to the left, but if we just want the distance, we get the magnitude. That's always positive. So these quantities are always positive, whereas these quantities could be positive or negative. Personally, I think removing the arrow leads to a lot of confusion. I think it would have been better to maintain these arrows, and if we just want to talk about, say, the initial speed, we use the letter u without the arrow. But that's not what has been done so I just want to mention that. Now let's consider vectors in two dimensions. Of course, we are working in the plane of the screen. We are going to consider the addition of two such vectors. The simplest type of vector addition to understand is the addition of two displacement vectors. Let's suppose that we have a particle at this position here, and sometime later it ends up here. So this is the displacement vector of the particle. Now how it goes from here to here does not matter. It could take any kind of a route. We're just interested in the displacement vector. Now let's assume that after some more time the particle ends up here. We are interested in the displacement of the particle relative to its original position. So that can be represented by a vector whose tail is here and whose head is here. Let's suppose that we call this vector A, and that we call this vector here B. Then we define the resultant displacement vector of the particle as the sum of these two vectors. So this vector is called A plus B. So this is not like an ordinary addition. The magnitude of this vector A might be 3, the magnitude of vector B might be 2, but we can see in general that the magnitude of vector A plus B is less than 3 plus 2, it's less than 5. Let's suppose that it's 4. So in general, the magnitude of vector A plus B is less than the sum of the magnitudes of vectors A and B. Now we could consider the sum of more than two vectors. We could have, say, 3 or more vectors. let's suppose that this is one of the vectors. Let's suppose here is another vector. And finally, let's look at this one here. Suppose that we want to get the sum of these three vectors. I'll call this vector C, I'll call this one D, and this one E. Now, we saw before that we can move a vector parallel to itself. So we're going to connect the tail of D to the head of C. Next, we connect the tail of E to the head of D. To get the resultant, we connect the tail of C to the head of E. So this vector is C plus D plus E. Now we can do that vector addition in a different order and we'll end up with the same resultant vector. So this time let's take the tail of E and join it to the head of C. Now let's take the tail of D and join it to the head of E. Finally, to get the resultant vector, we join the tail of C to the head of D. You can see that we get the same vector as before, but we can write it as C plus E plus D. So the order in which we add vectors does not matter. We'll end up with the same resultant. And this is true for more than 3 vectors, or any number of vectors. So in general, vector addition is commutative. The order of addition does not matter. So we just have this triangle here to consider when we are adding 2 vectors. Now, we could also indicate the sum of 2 vectors by drawing a parallelogram. I mean, the tail of vector B is at the head of vector A, but we could actually add 2 vectors by joining the tails together. So we can move vector B down so that its tail coincides with the tail of A now instead of the head of A. So this vector has the same magnitude as this vector up here and it points in the same direction. So this vector is considered identical to this vector here. To get the sum of these 2 vectors, well, I can just call it B, it's the same as this vector. We complete a parallelogram. So we draw a dotted line here parallel to vector A, and we can draw a dotted line here parallel to B and just draw in the diagonal of the parallelogram. So we can use a triangle construction or a parallelogram construction to get the sum of 2 vectors. Let's look at these 2 vectors here. For convenience, I'm going to call this one A and this one B, even though we've used these letters before, but it doesn't matter. First of all, let's look at the sum of these 2 vectors. Well, the tails of the 2 vectors are joined together, so we can construct a parallelogram to get the sum of these 2 vectors. So the resultant or sum of these 2 vectors has its tail here and its head here. Now let's consider vector A minus B. Well, we can actually write this as vector A plus vector minus B. What is vector minus B? Well, that's a vector which has the same magnitude as vector B but points in a direction that's opposite to vector B. So here it is. So I've put the tail of vector minus B at the tail of vector B. So to get A minus B, we could add vector A onto vector minus B by constructing a parallelogram. So that's how we sum 2 vectors when the tails coincide. So this is vector A plus minus B. Well, that's just vector A minus B. Notice, however, that we have a parallelogram formed here. Okay, this shape here is a parallelogram. This here has the same length as this here, and this angle is the same as this angle here, and of course this side is common to both of these triangles. show these two yellow triangles here. So we have two congruent triangles. So the sides and the angles are the same. So in particular, this angle here will equal this angle. But if these angles are the same, it means that this line is parallel to this line, and they're equal in length as well because the two triangles are congruent. Anyway, we don't have to worry too much about the geometry here. This vector here is the same as this vector here. So these vectors are identical because they point in the same direction and they have the same magnitude or length. So here's another way to get vector A minus B. Once vectors A and B have their tails coinciding, to get vector A minus B, we just join the heads of the vectors together. We then just have to decide, where does the head of vector A minus B go? Is it up here or is it down here? Well, we get that from the first vector that appears. So the first vector in A minus B is A, so the head of A minus B appears at A. And that makes sense if we just consider the addition of vector B and vector A minus B. If we take vector B and add it onto vector A minus B, well, we have our triangle construction, or the triangle law as it's sometimes called. We want to add vector B onto vector A minus B, so these one vector runs into the other vector, so the head of B is at the tail of vector A minus B, so we join the tail of B to the head of vector A minus B to get vector A. So from the triangle law construction, this makes sense, and also if we do the algebra, it makes sense. So the reason that the direction is important, of course, is that A minus B is not the same vector as B minus A. It's not like adding two vectors. If we add the two vectors, the order of addition doesn't matter, but when we subtract the vectors, the order does matter. B minus A would be a vector that points in a direction that's opposite to A minus B. So this vector here, the blue vector, is B minus A. We can get vector A minus B from B minus A by minusing vector B minus A. Remember, when we minus a vector, we reverse its direction. In the next videos, we will look at vectors in a coordinate system.